Oh, yes, update. We are gonna have a review on Monday from 3 till 6. So that means that in total, we're gonna have 4 hours. So get ready. We're gonna be doing a lot of practice problems. Now, since it's gonna be a long time, I'm gonna take it really easy on the actual like SI time. So it's gonna be from 1 till 2. So you guys can get something to eat for the review. So you all have glucose on your brains for the review, and we all can be okay for the 3 hours. So you guys can do that. It's gonna be 3 until 6, the actual review, but I still have SI from 1 until 2. So in total, it's gonna be like 4 hours. So yeah. Here's the thing. Oh, the review is gonna be in the physical science building in 109. So it's the building right across from us right now. And it's the first room that you're gonna see as soon as you open it. So I think so, yeah. I'm not quite sure. But I'm not sure if they have the computer, the microphones, all of that. That's connected. So I'm gonna try to record still. Like I can just record it on my laptop and maybe like wear one of my AirPods for the microphone, and that's it. So hopefully we can make it work. I will try to do it, yes. But again, remember, if the internet is not that good as well, so there's that. But so far, before we start reviewing, yes. Yes. So don't worry, I'm gonna send it probably like right after class. So you guys are gonna have that. I already started working on the review handout. I'm gonna do not only practice problems, but I'm also putting a little conceptual part so you guys are aware of everything. So it's gonna be a review, very dense review, let's say. But actually, raise of hands, how comfortable do we feel with chapter 12? Who feels comfortable? Raise your hand. Just one. Just one. Two.
Oh yeah, epoxides, that was over.
Ethers, epoxides, those guys are on the exam. Yes. But how comfortable do we feel with those ones? Who feels comfortable with that chapter? Not that many. That's okay. It was a long time ago. What about chapter 13? How comfortable do we feel? Okay, that's better. What about chapter 14? I was expecting all of you to raise your hand. Okay. So this time we're just going to be reviewing basically the handouts. So we're going to go back to chapter 11, 12. And then if this loads, let's see. Okay, so that was Greenier's. Protecting groups, that was technically on the first exam, so you shouldn't get tested on, but sometimes he likes to show multi-step synthesis. So that means that some old reagents can come back, especially protecting groups. So just keep that in mind. I'm not sure if he's gonna include them in this exam, but just in case, keep those in mind. Then oxidation, it wasn't at all on your first exam. So just in case, I'm gonna go over this right now, just so we're on the safe side. But oxidation, what's the definition of oxidation? You increase the amount of bonds between carbon and oxygen. Exactly. That's how we know we're oxidizing something. So that means we're always going from an alcohol to some sort of carbonyl group, right? Now, we had a lot of reagents for this portion, but the easiest way to memorize them is just memorize the 2 weak oxidizing agents, and that's it. Because the strong oxidizing agents, they all have a high content of oxygen. So as long as you memorize the weak ones, you should be good to identify the strong ones. And then we know that depending on what kind of reagent we have, we're going to get different products. If we start with a primary alcohol and we use a weak oxidizing agent, we always create an aldehyde. But if we use a strong one, we create a carboxylic acid. If we start with a secondary alcohol and we use either weak or strong, we're going to create the same exact carbonyl, which is going to be a ketone. So this part was mostly memorizing again. might or might not be on the exam, but just in case, any questions on oxidation?
No, it's just that this was sliding in and make that sound.
Oh. Don't worry. Anyways, questions on oxidation. And for those of you who just came in, we're basically just going to be reviewing the SI handouts. Chapter 15 is not at all in your exam, so I'm going to stop covering it. We're going to get back to that after the exam. So, yeah.
So you said oxidation was when
You increase the amount of bonds between carbon and oxygen. Yeah. Exactly. Okay. Now, this one is going to be for sure in your exam. Your DOS reaction. Do we remember that one? Yes. Anything that's ethers or epoxies related, it is going to be on this exam. So do we remember the West reaction? Barely. Okay, let's start with the basic steps. We only have two major steps. The first one, very simple, acid-base reaction. So that means that I need some sort of base, like NaOH in that case, and an acid. In this case, the only acid that you're going to see for this reaction is going to be some sort of alcohol group. In that case, it was just ethanol. Now, the second part of the reaction is always going to be SN2. So that means that once our base, sorry, our acid gets deprotonated, we are creating the conjugate base, right? We are going to have a negative charge, so that means that it's also going to be a good nucleophile. So to do the SN2 part portion, we just need an alkyl halide, and that's it. 12. Yes. So, are we remembering a little bit? We know the reagents, we know the main steps, somewhat, not that good. Okay, it's out of your heads right now. Okay, so remember, this reaction is always going to be creating ethers. Now, it can be linear ethers or it can be cyclic ethers. Okay, let's cover that part. How can you make a cyclic ether? What kind of molecules do I need? Yuli. It's going to be an intermolecular reaction. So that means that everything has to be within the same molecule. More specifically, your acid, your alcohol group, and the halogen, they have to be in the same exact molecule. The only reagent you're going to be provided is the base. That's the part that's going to trigger this reaction. Okay, so far questions on West, on your DOS reaction. Very simple. It's basically combining two reactions that we learned. I'm sorry? Yes, this is one of the ways of making epoxides, but it can also make any cyclic ethers. Dr. West usually doesn't give you like giant compounds. That's more like Dr. Roche style, but yeah. Yes. Yes, it can be any H. As long as it's any sort of base, it's good to go. Okay, before we do that, let's talk about our ethers. So we know how to make them now for the West reaction. To break normal ethers, they're going to be broken in both acids and bases. What do we think? No? What's going to be the cleavage? Part of it, yes. But remember, ethers, normal ethers, those guys are only going to be cleaved with acids. Only with acids. The only reason why epoxides are cleaved in both acids and bases is because the molecule is very reactive due to the ring strength that we have in there. So again, remember, let's say that you're given this molecule over here, that's cyclic ether. That one is not an epoxide. Now, if instead of having HBr, you had NaOH, it's going to be no reaction at all. It's going to be stable in bases. So keep that in mind. That can be a conceptual question. And then for acid cleavage, what was the ranking? It's always going to be 3-1-2. Exactly. What about base cleavage for epoxides? 1, 2, 3. Now, we know that the intermolecular West reaction is one of the ways that we can do our little epoxide, right? Now, the other way that you have to be aware of, it's double bond plus some sort of peroxy acid. How do we know we have a peroxy acid? What was the main part that we see? It's going to be CO3H. So remember that one of the reagents is pretty small, so it's pretty easy to see. But in this case, remember that MCPVA is quite long, and again, you might be given this in condensed formula. So as long as you're able to identify that CO3H portion, that's going to tell you that you have a peroxy acid. Now, if we remember this reaction, you don't have to know the mechanism at all for this one. The only thing that you have to know is that it's a syn addition, so that means that both bonds that are making the epoxide, they have to be on the same plane, and that's it. So far, questions? Yes. It can be both ways. You can start with a halohydron formation, so we start with a double bond, and then we create our actual molecule needed for the West reaction, or he can just give you the starting molecule, so OH with chlorine. So yeah, so you should be aware of both ways. Okay, that's the ranking that we just talked about. Okay, do we have questions on the mechanism for breaking epoxides? Yes. No, yeah, she just said yes.
For the second, reaction, so for the last step where you flip the orientation
Mhm.
of halogen.
Yeah.
Yeah, it's that. So essentially, explain that really quick.
So we're gonna be flipping that configuration because we want to show the backside attack of an SN2 mechanism. So we know that our base, that oxygen with a negative charge, sorry, our nucleophile is gonna be doing the backside attack to the carbon that has the chlorine because it's gonna be an anti-bonding attack, there we go. That means that we're gonna be flipping the configuration because once we do that, we kick out chlorine and that's how the stereochemistry is changed. So it's like a normal SN2 reaction, we just flip. Okay, how many of you actually remember this part, how to break epoxides? Just raise your hand if you remember. That's all we know. Okay, it's gonna do its thing. Does anyone feel comfortable with breaking epoxides? Neither acid or base cleavage.
It's like someone going over this and it was like super simple. Yeah. It comes back around, done, right? But it's like, yeah.
Okay, so we're definitely gonna review this one. Before we do this little guy, the very last thing, it was the easiest IAPAC question that you might get. And again, it might just be one, but crown ethers, we know that the big number that goes in front, it's including both carbons and oxygens. The small number that goes before ether, that guy is just accounting for the oxygen. So don't mix them up, okay? And we're not counting hydrogens. Yes.
So just be time. So big number is the total.
The total amount of carbons and oxygens, yes.
And small number is hot.
It's just pure oxygens, yes. We're never counting hydrogen, so keep that in mind.
One thing I didn't remember that one.
Yeah. So as long as you just count the oxygens, you can just multiply them by 3, and that should give you the big number. So you guys can save some time. Okay, what happened? Let's fix this. Like, no, he's not gonna give you the Crown-Sink condensed formula. So yeah, no. That would be awful. Okay. Let's see practice problems on epoxides.
Can you just go back to the West reaction?
Yes. No, that's not the chapter. Actually, let me start drawing out the molecules in here. So there's two reactions on the board in red. Give them a try on your own for 3 minutes. Show me what's going to be the product and show me how it's going to look like in condensed formula. I can just take like about 3 minutes. Yeah. Show them to me in condensed formula. Okay, the first one, don't show me in condensed formula. Yes. Show me the bottom one in condensed formula. This is the important one. And we had a question in the middle, or no? That was for the West reaction, right? Let's go back. Okay, so in this case, we don't have sodium hydroxide, but still, same process. That base is going to be provided for you. It didn't come from anywhere. We are providing it. We're not creating it. Okay, let's see. That's okay. There shouldn't be two products.
Oh, no, never mind. The right side. I'm just gonna.
Okay, can I have 2 volunteers? I have one that's kind of sure. Go for it. And then do you want to do the second one? Do you have it in condensed formula?
Oh, we condensed formula.
Okay, so you guys can both check each other out. Yes. Oh, okay. The first one, you don't have to draw it in condensed formula. No, you don't have to show it in condensed formula. Usually whenever he has epoxides, he just does them linearly. I just did that one just because.
No, there's a carbon there, it's not connected to the oxygen, so that's not good.
So I don't know how I got this.
But we got
No question.
don't question it. Did you get the same product? Can you draw it out? What do you got?
It's better get it wrong now than on the test.
Yeah, it's better to get it wrong here. Oh, that was pretty. Great job. First of all, both of you, great jobs. Now,
Wait, I got it.
those are two different products. We had something completely different.
Yeah.
Okay, so first of all, what kind of cleavage am I doing? Acid or base? Acid. Okay, what's the ranking for acid? It's 312. Okay, so if it's 312, how do I use that rule? What do I have to look at?
The acid rather on tertiary or
So that means that
acid.
you're only going to look at those carbons that are directly connected to that oxygen. The one on the left has 1, 2, 3 R groups, which means that it's tertiary. Remember, the bond between carbon and oxygen, it doesn't count. The one on the right, it has 1 R group, so it's primary. So which one is going to be preferred to be cleaved, left or right? It's going to be the left one.
I mean, yeah.
So we're going to cleave this one. So that means that the oxygen in here for our epoxide is going to be hanging on from that primary carbon. So it's going to be over here. And then whatever you have on the arrow, this guy is going to be connected where you're cleaving it. So that's why we end up with the little ether in there. Do we all see it? No? Okay, we're processing it.
Oh, so the OH is coming from
It's coming from the epoxide.
it's coming from the original O.
Mm-hmm. Yep. That's why I color coded them as well. Oh. Always look at the color coding. Okay. Questions on the first one? It's 312. No. That was for Dr. Roche. I said both rankings and I specify them. If you're watching this recording and if you're taking Roche, it's 321 for acid cleavage. If you're taking West, it's 312. Don't ask me why. That's just how it is. Okay. Are you good with the first one? Not yet? Yes.
So if you're cleaving that third, the tertiary carbon, would it O end up on the primary side?
That oxygen is on the primary side from the epoxide.
Okay, so my question is, where did the second carbon come in from the OH?
There's no second carbon in there. Okay, so let's redraw this guy. Okay, so I know that this guy on the left was tertiary, this one was primary. So that means that I have to cleave the left one. So we basically can just erase this bond and we're gonna see how that oxygen is gonna be hanging from that primary carbon. There are no extra carbons on the product in here. This guy, it's still the primary one. Primary, this guy was tertiary. Now, once we do that, technically we're gonna have a carbocation on position 3. Okay, at this point, whatever you have left off here on the arrow is gonna go over there. So this guy is gonna be your intermediate. We're gonna have O minus so far, and we have OH with 1 and 2 carbons. So very last thing is basically just to move that hydrogen to the other side, exactly. So once we do that, we end up with our product, or oxygen. Oh, and there we go. Those two are the same exact thing. So questions? Does that make it better to see? Okay. Yes. Great question. So whenever you see H plus either at the top or at the bottom of the arrow, that's always representing an acid cleavage. If you see anything else, especially any ionic bonds, that's going to be your base cleavage. Yes. Yeah, the second one is a base cleavage. Yes.
You said earlier that cyclic ethers can only be made with acid.
Cyclic ethers. Cyclic ethers that are not epoxides. Epoxides, those guys are special. Epoxides, that's a little triangle looking structure that can be cleaved in both acids and bases. If we have a ring with an ether in it, and if it has more than 2 carbons in it, so we don't have the triangle, then it can only be cleaved in acids, not bases. So for example, let's say that I have
You have a cyclic ether carbon.
with 2 carbons, so that means that this guy is your epoxide. Remember, the triangle looking structure, it's always going to be your epoxide. If you have something that looks like a square or a little house or your little benzene group, those guys are just going to be cyclic ethers.
Okay, so the epoxide first that time.
Yes, both in acids and bases. And then your normal cyclic ethers, those guys are only on acids. Mhm. It's 1 to 3. Volunteer for the second one. Yeah, go for it. Do you want to do it? Okay. Let's give them 1 more minute before we solve it. And just wait a few more seconds so they can finish writing their notes, and then you're good to go. This one, it's a tertiary. No problem. Okay, we're ready? Okay, you're good to go, Emily. The second one is not an acid cleavage, it's a base cleavage. Yes. Acid cleavage, we see some sort of H plus either at the top or at the bottom of the arrow. And then whatever else you have is just a base. Or you can also see that you have some sort of ionic bond in there. The mechanism is slightly different, yes. They both have the same steps. So they both include a nucleophilic attack and they both include an acid-base reaction. The order is different. So for example, base cleavage starts with the nucleophilic attack and ends with acid-base. But acid cleavage starts with acid-base reaction and then ends with nucleophilic attack. But again, you're not going to get asked about the actual mechanism. 1, 2, 3, that's for base cleavage. Okay. Great job. Okay, so let's look at this one. Tertiary, that's secondary. So we know that the ranking, it's going to be 1, 2, 3 because it's base cleavage. So, yes, base cleavage is the same for both professors. You only have to be careful with acid cleavage. Okay, so we have this little guy. So that means that the oxygen minus is going to be over there. Beautiful. So yeah, the oxygen from the epoxide is just going to be hanging from the tertiary one. And then on the other side, the side that we cleaved, the secondary one, that's where we add what we had on the arrow. Okay, did we all get the same answer? Did we give it a try? We did? Okay, that's good. At least we tried it. Okay. Yes. Yeah. Because you can basically redraw the same structure and then just start erasing this bond, and that's it. So we know that we have a carbocation here, O minus there. So you can pretty much figure it out from there. Great question. No idea.
What's different with second? What exactly? Why do we choose second over third?
In this case, because it's a base cleavage, so we prefer to cleave secondary. Yes. That was the main difference. The first one was acid cleavage. They have a different ranking than base cleavage, the one at the bottom. The exact reason why it's in that specific order.
So for the second step, that other oxygen.
Purple or orange?
Oh, never mind. I got it.
Okay, we got it. Okay, and then let's check the condensed formula in here. So CH3, CH2, CH. We have this portion. And then we have carbon with. Great job, Emily. You got it. Okay. So far, any other questions on acid or base cleavage for epoxides? We're good now? Are we starting to remember a little bit? Okay, slowly, but we're getting there. Okay, chapter 13. It was all about pi systems, right? We talked.
I did work. Oh, actually, maybe the pipe. That's like on.
Exactly. So let's talk about chapter 15 over here at the bottom. Chapter 13, because that's where we started talking about the pi systems.
Yeah.
We have 3 different ones. What was the ranking for them? So yeah, remember the conjugated system, that's the most stable out of all of them. Isolated, next one, accumulated. Okay, last one. How do we know that we have accumulated system? Exactly, they're right next to each other, they're clashing each other. How do we know we have an isolated system? More than 3 bonds away. What about conjugated system? It's like a little sandwich, exactly. So yeah, we were talking about sandwiches and tutoring, so yeah. Okay, those systems. So if we're talking about double bonds, we have the cis and trans configurations, right? What are the proper terms that we have to use for this class? No. No, before the super. Before the super. We are not gonna say it's gonna be easy, exactly. We're not gonna be using cis and trans. We're gonna be using E and C. So double bonds, they're classified C, which is cis, or E, which is trans. And then the conformation, that's where the supers comes in. We have two, right? We have super cis and super trans. And am I gonna see those guys in all of the 3 pi systems? Where am I gonna see them only?
Dying.
Which are, what kind of system are dyings? No.
I don't know.
Okay, so which one did you say? They are conjugated. The dyings that we are looking at, that reaction, they are conjugated now. The super cis and super trans, they're only gonna be for conjugated systems. So just keep that in mind. We're not gonna see them for isolated or accumulated. Now, if we're looking at the overall stability of a molecule, the more trans you are, the better it is because we have less steric hindrance overall, right? So let's go back to the handout at this point. 13, where is it? There we go. Okay, so in this case, all of those molecules are conjugated, right? We just see the little sandwich pattern. Now, the more conjugated you are, the more stable you are. That's why number 4 was more stable out of all of them. And then what was the main difference between molecules 2 and 3?
2 has like, it's like an 11 versus.
So yeah, you're all correct. The first molecule, there's a lot of ring strain in there. It's not the ideal molecule in there. And then the secondary one, yeah, we have the alytic position. That's awesome. But in this case, we would also call it the benzylic position, which means the same thing. Okay. Take a quick look at those 5 molecules in there. Does it make sense why we chose that specific ranking, or do we have to go over it again? It's completely okay. Just take a quick look. We're good? For this, no.
There wouldn't actually be any.
Exactly. See? This one, it's cis because we're just looking at the double one. It's not super cis. It's just C, so it's just cis that one single double bond. And then remember, whenever we have terminal double bonds, we don't have 2 R groups to compare the configuration for. So that means that we're not going to be able to tell if it's cis or trans. Okay, so that only applies for mono-substituted double bonds. Okay. Next concept that some of you have forgotten is UV spec. What was the 3 main aspects that we're looking at? What was the little chart that we made, the little ranking that we made?
Wavelength.
Wavelength, conjugation, and energy. Okay, what was the actual trend? Exactly. The more conjugated you are, the longer the wavelength it's going to be, and the less energy you're going to have. Remember, because if you're really stable, you're not going to be that reactive. So there's not going to be that much energy in that molecule. And then if you're trying to figure out the complete opposite, just flip the trend, and that's it. So questions on UV spec. So far, we're good. Okay. Yes. The more conjugated, the less energy. Yes, but the longer the wavelength. Okay. Let's say that I'm gonna give you this molecule over here. Okay, now at this point, we know how to apply the molecular orbital theory in 2 ways, right? We know the linear way where we just stack them on top of each other. And then we know from chapter 14 that if it's a cyclic structure like benzene or cyclobutadiene, we have to match up the carbons. In this case, if I'm giving you that molecule in pink on the left, how is the molecular orbital going to look like? Am I going to place them together or am I going to stack them? I'm going to stack them. Why? It is a ring.
Overlapping.
Is not fully conjugated. That was the main portion. If a molecule is not fully conjugated, you're just going to stack them on top of each other. If it's fully conjugated, then it's going to be, you have to match them up. Yes.
Just to reiterate, you said, let's say that peak right there on the pentagon is either a cation, or a radical. That means it is fully conjugated.
Yeah. Okay. Okay, this is not working. So far, any questions on what we just covered today? We're good? Okay, so I can work on your review now, but we want more practice problems on which chapter? 12, 13, or 14? Mostly with the reactions? Okay, mostly reactions.
The rest is just conceptual.
The rest is just conceptual? Okay, yes.
So these charts, because I was kind of doing that at home. What's it called? Is that going to be like a test on the question on the test?
For those kind of questions?
These little charts down here because
No.
Oh, no, he's not gonna give you that.
No, you're not going to be asked to draw the energy diagrams or anything like that. He's just going to be asking, for example, for that molecule, how many pi electrons do you see in the HOMO orbital in the excited state? It's just going to be one. He might ask non-bonding, bonding, anti-bonding, everything is fair game. In a way, yes. So at the end, the only thing he's going to be asking is for whatever numbers you see at the bottom of that chart. Okay? He's not going to be asking to show the diagram. Yes? This review on Monday. Oh, yes. So update. In case you got here late, the review is going to be on Monday in PS 109. So it's the room like right across from us. And it's going to be from 3 until 6. So that means that we're going to have a total of 4 hours. So on the first hour, the actual SI time, we're going to take it really easy, really slow. You guys can go and get some food because we're going to stay here for a long period of time. So that's completely okay. Okay. So please get food. You need glucose to study.
Monday.
Oh, yeah, you're right. Yeah. We do have an hour break. I forgot about that. So yeah. Yes. The review starts from 3 until 6. So yeah, it's a long time. So in total, we're gonna have 4 hours of review. That's just for exam 2. On the third exam, I'm not sure. My plan was just to make the review 3 hours, but there was a little miscommunication with me and my supervisor. So we have a total of 4 now because I forgot about SI.
Oh, okay.
So yeah. No. Yes.
But why is there 2 in the ground state? Why are there 2 antibody molecular orbitals? There's empty.
So remember that we always need we need the same amount of bonding orbitals that we have in the anti-bonding orbitals. In that case, we have an even number of orbitals, so that means I only have anti and bonding orbitals, no non-bonding. Exactly. That's where the non-bonding comes into play.
Okay.
So it just works out like that. There's always one number of anti and bonded. And then if there's an odd number, it's one non-bonded.
So yeah, it's like what we saw in here. In this case, we have an odd number, so we have 1 on bonding. But we're going to be talking about this more on Monday. So get ready. Yes. Yes. We're going to go over them on Monday, actually, because we don't have freestyle. Yes, Mickey. The condensed formula?
thing.
Yeah, no, I'm gonna make the review with condensed formula, but yeah. I'm gonna try to record it. If we don't have like the technology in the actual room, I'm gonna try to record it with my laptop. You would just have to wait like until that night. I'm gonna post it like right away, as soon as I get the actual recording. Mhm.
There aren't any electrons in the non-bonding orbital, right?
Sometimes you can, like in the allyl radical.
Like I said, if there's a radical?
Yeah.
Only if there's a radical?
Yes. Sorry, and the anion as well. I forgot about that guy.
And ion meaning negative charge?
Yes.
Okay.
So look at those two guys.
So there are 5.
Yeah.
So,
Yeah, I get that.
Okay. So.
good. Now we're actually over time in SI. So Alex, I'll talk about that on Monday for sure. So don't worry. It's gonna be for sure Monday.
Understand, there are 5 orbits, there's 5 orbits, right?
Okay, get that.
5 orbits, 5 orbits. On number, you have to be number by subtracting 1 non-bond.
Oh, okay, so then, yeah, 4
Right.
bonding, 1
Right.
non. Right, so it'll be